I still have to write it. If you got a real good problem that you're like, man, this problem is fantastic. It's burning a hole in my soul and I want to solve it where it counts, just shoot me an email. Okay. Now, the last exam covered up through chapter 28, but some chapter 28 will be on this exam because we only did a tiny bit of chapter 28 on the last exam. So some chapter 28 material will be covered. And then we will go up through chapter 31, which is circuits. Okay, so from chapter 28, though, if you recall, and this is one of the most important equations from chapter 28, is that the potential, V, is equal to U over Q. That's the potential energy over Q. Now, what you'll note about this is this looks analogous to E equals F over Q, right? Only without the vector symbols. So this has similar relationships here. Now, one of the most important things, though, is for a point charge, the potential looks something like this. 1 over 4 pi epsilon naught times Q over R. Okay? So, and you know, this will be on the equation sheet, but you're going to have to know that that is the potential of a point charge. And the reason where that's, yes?
Are you going to be putting up the Sula sheet before the test tomorrow?
If I have time to, but most likely not, because I have no time. But I'll try and get it up as soon as I can. Okay. So, also, we know that if you want to find the potential, that's equal to Q times V. So if you can find, the potential energy. So if you can find the potential anywhere in space, you can find the potential energy just by multiplying by Q, the charge that you're putting in that potential. Okay? So remember, potential is something that fills space. Potential energy is when you put something in that space. It's stored between the electric field interactions of two charges. Whereas potential is just a way to describe this distortion of space, just like the electric field is a way to describe the distortion of space. But what's the difference between an electric field and a potential? Yeah, one is a scalar. Which one's a scalar? Potential. Which one's a vector? That's right. So if I have some charge, it distorts the space around it. If I say, what does a vector field look like? Well, it looks like a bunch of arrows kind of pointed out like a porcupine, right? But what does the scalar field look like? That is the potential. And it's a bunch of numbers in space, a bunch of scalars that permeate all of space that tell you about the strength of the field. Okay? All right, so now one thing about this is the relationship between potential and potential energy. Now one thing about the potential is that like electric fields, it obeys superposition. So, in other words, you can go ahead and add all of the potentials up to find the potential at one point in space. And I had to do this for 2 points for two charges in space, right? Remember, this is the last question on the last exam. I had 2 points in space, like this. They were positively charged, and I asked for the potential right there. And you just take the potential from each of those point charges and you add them up. In fact, you can add up as many as you want. That's a bad sum sign, sorry. And it becomes the sum of all of the potentials. So that's 1 over 4 pi epsilon naught times qi over r sub I. So you just add up all of the potentials from all of the point charges and their distance from the point in question. Now, where does this go from here? Where does this go from here? We go from 2 to many to, yeah, an infinite, a distribution, right? I'm going to get rid of some of these notes because it's a lot of them. To some distribution. So for a continuous charge distribution, this becomes an integral. So, you know, I know how to do these. Do you want me to do a ring of charge, or do you want me to do a line of charge?
Line.
A line?
What's going to be on the test? Or more like what's on the test?
Whichever one I don't do.
Okay, well,
Do a
which
ring.
one?
Do the ring.
You do both of them, so either of them will be on the test.
Well, then I'll come up with like a box or something.
Okay.
Do line.
A star. I like it.
No, I'm just kidding.
William's got a good challenge. A star of charge.
A star with an infinite
All
amount
right.
of points.
All right, let's take a vote. We're a democratic class.
Circle.
Line of charge, raise your hand. Ring of charge, raise your hand. That's a pretty even distribution. This is
Did you
Looks like you gotta do both.
no, we got a lot to cover. All right, I'll do a line. I did ring in my notes, so you've got that one. So if we have some line of charge like this, okay, and we want to find the potential to at some point, maybe up here, P. Okay, we'll say this is the x direction, we'll say this is the y direction, and let's say that some charge q is distributed over this rod. Now this distance here, the length of this rod, I'm going to call that b, and this distance here, I'm going to call that a. Now, like before, it's always wise to find some little chunk of this rod that represents our small dq of charge. Okay, so that's our small little infinitesimal bit of charge dq. Now, there's also some geometry associated with this. There's this distance here, and that's r, the distance between that little chunk dq and our point in question along the y-axis here at point P. The other thing we need is the distance on the x-axis to this point right here, which I'm going to conveniently call x, and that is what we're going to integrate over, right? All these little dq's at all these distances x, so x is what is going to change. That makes this distance r equal to what?
Squared.
Square root of?
X squared plus a squared.
What is it?
X squared plus x squared.
Yeah, x squared plus a squared. Okay, not b. There's no b in there. Okay, so now we've done a little bit of the groundwork. Now, before, remember, when we calculated the electric field at some point, we drew some little vector here, dE, that represented the electric field from this little chunk of charge right here. But in this case, we're trying to find the potential. And the potential is a what? It's a scalar. So we just find some little dV right there. And it doesn't have a direction, and it doesn't have a, well, it has a magnitude. It's just a scalar, okay? Some scalar dV at that point due to this little chunk of charge dQ right there. Now what we need to do is add up all these little chunks of charge dq and their contribution, and really the only thing that changes is the distance r, but there's no direction associated with it because it's a scalar. Now, like before, we have to go ahead and set up our linear charge density, which is going to be dq over dx. I won't go into this too much. You know how this is done. This becomes dq equals lambda times dx. I'm going to need that. The next thing is I go ahead and look for the equation for the potential due to a point charge, and we're going to turn that into something with a dq in it. So for a potential, let's see here, v is equal to 1 over 4 pi epsilon naught times whatever q I have divided by the distance away from it, right? That's for a point charge. But that is now going to become a dq. So we have some little dv, and that's going to be 1 over 4 pi epsilon naught times dq over r. All right, well, I already solved for dq. I already solved for r. That's just a geometric thing. So I can go ahead and plug what I know in, and I get this is equal to 1 over 4 pi epsilon naught times, let's see here, dq, that became lambda times dx over r. That's square root of x squared plus a squared. Okay, next thing I'm going to do is integrate both sides. Integrating this side, I just get a v, right? I'm just adding up all those little dv's, and I get the total potential at that point. And that's equal to, well, here I can pull out anything that's a constant. That's going to be lambda over 4 pi epsilon naught times the integral. But the limits of my integral are going to be what? 0 to b. That's the length of my rod. 0 to b. And that's the integral of dx over the square root of x squared plus a squared. Okay? Now, from this point, you can either do this integral by hand, or you can look it up in a table of integrals. But for the most part, this is what you want right here. Okay? Now, this integral, I think, becomes, this is lambda over 4 pi epsilon naught. It becomes the natural log of x plus square root of x squared plus a squared from 0 to b. Okay? Which you can go ahead and further reduce. Let's see here. That should become natural log of something like b plus square root of d squared plus a squared all over a. You might want to check that. I'm not positive about that. And that's it. These are easier than the electric field problems because there's no direction you have to take into account. Remember, we had to do cosine of theta, figure out what cosine of theta was in terms of the geometry of this triangle, and then take that component. You don't have to do that with the potential because it's a scalar. Okay? So that's how those guys go. Any questions on that? Yes?
Do you have to solve the integral in the test, or do you just do that in integral form?
It depends on what I ask for, but if it's an integral like that, I don't know how to do that integral by hand. So if I don't know how to do it by hand, then I won't ask you to. And I haven't done integrals by hand for a while. But it's totally within reason for me to give you a small table of integrals and say, okay, well, here's a table of integrals, and then have you solve it, right? Which is basically what I did right here. I didn't do that in my head. Okay, any other questions on that? Okay. Now, if I were to plug in a bunch of numbers here, let's say like I had b, and I had lambda, And lambda, right, that's actually equal to Q over L, or I guess B in this case, the length of this rod. I go ahead and plug numbers back into this. From there, I could actually calculate the potential. And the potential will be something like, well, what would the potential be? What are the units? Volts. Okay, so it's something like 2,000 volts. I could then have you find the potential energy of something. To find the potential energy of something, how do I use this result to find the potential energy? Yeah, you use that over there, right? U equals QV. If I want to find some change in potential energy, or if I want to find some velocity, like I did on the last test, you use conservation of energy. You plug in QV for your potential energy, initial and final, and then you go to town with conservation of energy. Okay, so that's how something like that would tie in to a problem like this. Once you find the potential, finding the potential energy, it's pretty easy. It's just you just multiply it by Q. Okay. Let's see here. I don't know where this chapter ends and the next one begins. Ah, there it is. Okay. The next thing is chapter 29. And they open chapter 29 with this big picture diagram that I really like, because it ties everything together nicely. So they call it potential and electric field. All right, so the big picture looks something like this. So we have four corners of this square laid out so far. Down here is E. Okay, that's the electric field, and that's kind of where we started in this class. Or maybe we started up here. We started somewhere over here. Okay?